All right, so let's talk about binary search. This is a tough one. It's meant to be a tough one. As it says here in the README, it's an extraordinarily common interview algorithm. You'll find it on a lot of job applications. So the goal of it is to find the index of a value that you pass in compared to a sorted array of strings or integers. So the idea is and they have the basic premise of the algorithm for us. So we're searching for number defined in a search set of sorted values. You need to find the middle value. And if the number we're looking for is equal to the middle value, then we found it. If the number defined is less than it, then we split it in half and repeat the algorithm on the new subset. And if it's greater, we do it with a different subset. And we keep on narrowing it down until we find the number defined or the index number, or return -1 if it doesn't exist. So how did people feel about this one? Was this a fun one or a frustrating one?
Well, once you figured out what the algorithm was, it wasn't terrible.
Mm-hmm. Yep. So it's one of those things that you solve, once you solve it once, it gets pretty simple. So one thing I was actually thinking is, did people solve this iteratively or recursively? Because this can be done either way.
We did both in Python.
Mm-hmm.
We were supposed to do it recursively.
Yeah, Dan and I thought, based because of the day and challenge, that it was that recursive was required.
Yeah,
Recursive is definitely way harder.
Yeah, recursive is harder, and like I said, anything you can solve recursively, you can also solve iteratively. And I was looking at the instructions, and I don't think we ever actually explicitly said it had to be recursive, but it was recursion day, so it makes sense. So let's solve this recursively together. So first off, I'm going to solve this in Python as well, because I feel like it. So before this time, I'm actually going to set up unit testing, because I actually want to do this the right way. So I'm going to comment all of this stuff out. Make sure I import unit test. You can say class test binary search unit test.test case. I have too many T's in there. There we go. All right, so this way, I want to, the examples they gave us are 1, 2, 3, 4, and 5, and 1, 5, 7, 2, 3, 8, and 4, 9. So we can say test, test small array search. We could do self.assert equal. Well, first we need to define a array. So test array equals 1, 2, 3, 3, 4, and 5. Then we could say self.assert equal. If we're passing this thing, let's see, what order did it want it in? Or we can just look down here. What am I doing? So if we wanted 1 and test array. Nope, duh. Binary search. That should come out to be 0 because it's the first one, right? So look at this. I could just keep on writing tests. Too many functional arguments. Oh, because we haven't figured out binary search yet. That's fine. So if I keep on writing functions to test all of these cases, does anyone see a kind of a code smell when that comes with that?
You were repeating test array?
Yep, I'd have to define test array over and over again, which isn't a huge problem, but it's annoying. So what I'm going to do is I'm going to use a method that's built into a unit test called setup, I believe. Def set up, or is it set up? Nope, setup. And does anyone know what setup does?
It basically processes whatever you have in the function named setup before each test. So before each test is even ran, that setup function is ran first.
Exactly. So if I have to test multiple cases that are all going to work on the same data set, I can just say before every test, define something called test array that happens right here. And this is especially good if you're working with destructive functions, because then you'll have a fresh version of it every time. Right. Why is self? So I could do def, test small array search 1, and then just copy this line and just say 1 should give us an answer, 2 should give us an answer of 1, and so on and so on. Why am I getting my linter is weird sometimes. Okay. And I can just, repeat this a few times. All right. Now what's it saying? Okay. Okay. I think should it be self.testArray? Yeah. So now it's self.testArray. Or
we ended up setting it at test array as a class variable at the top, but if you do that, you can't use self. You have to actually call the class, I think.
yeah, let me double check this, because sometimes, so unit test setup. You have to, I see. So it's a lot like an init. So I'd have to say self.testArray equals that. There we go. That fixes the problem. And it's still giving me that, but that's fine. That's what it's supposed to do. Let's do one more of these. If I want to find the last thing in the array, so I'll call this self-array search. I've not been naming these well. One sec. If I want to get the last thing in the array, which is 5, I should expect an answer of 4. All right, so we got some test cases here. And we'll expand on this more as we test things out, but I want to get to the actual logic here. All right, so again, let's get to our pseudo coding now. So we know that we have to define binary search that takes a sorted array and value to find as arguments. All right, so knowing we want to approach this recursively, what do we need to figure out?
Our base case.
Yep. So what is our base case here?
If the middle value is equal to the value defined, or your array is 0 length.
Yeah. So if value at middle index equals value to find, return middle index. And if length of array if length of array, is that what you said?
I don't know what you're calling it yet, but sure, length of the array.
So that implies that we're going to be chopping the array down to size as we run through our iteration, our recursions. All right, so I'm seeing a little problem with that with there because we want to return the index number in the original array where we found that value. And if we're chopping the array down to size, then the index numbers are going to change every time, aren't they?
Yeah, we took care of that using a default variable or default input,
Okay.
and that was changing to account for that shift in index.
All right, so let's talk about, okay, so, all right, let's take this approach then. So the length of the array is 0, return -1. So we need to come up here to fix this thing. So we also need an optional argument. So what did you call that optional argument?
Index offset.
Index
Yeah.
offset. And what is the default value of that?
0.
Yep.
Okay. So in that case, we've got value at middle index equals that. Now, if we're not in our base case, what do we do?
You check if the middle value is larger than your value defined.
Yeah, we're missing a step here though.
We need to divide the length by 2
Mhm.
of our
Right.
array, and then take the int value of that, or the floor of that.
Yeah, we need to find the middle index before we compare anything.
Yep.
So we find the middle index by comparing the length of the array and doing what again?
Divide by
Right.
2 and take the integer of that.
Take the floor.
Yeah, divide by 2 rounded down.
Also, we're at this point assuming that the array that's passed in. Okay, yeah, I see it now. I'm sorry, I was thinking it wasn't sorted yet, so we would need to ensure that it is sorted if it wasn't sorted.
That's a good point. So it did say down here, look at one of the examples it gave us, this is a non-sorted array. So let's just assume that we're not going to get a sorted array and just make sure we sort the array. And we're not going to use an algorithm for that. We can just use a built-in method. So sort array, find the middle index of the array by dividing the length by 2, rounded down. All right, and then we have our base case. And then we have to say, all right, so if value at middle index is less than value defined, what do we do?
You want to pass recursively the, sorry, you want to make your offset equal to the middle index.
So offset equals middle index.
And it's actually going to be middle index plus 1.
Middle index plus 1, how come?
Well, this is where when we're doing the comparisons with the iteratively, because we're running both of them, we're always off by the number of times that it goes since the right slice. If it goes to the left, it doesn't really affect the offset at all. But every single time it goes to the right, it was always off by 1. So if we went to the right twice, it'd be off by 2. If we went to the right 3 times, it was off by 3. So basically, for each time it was sent in recursively, excuse me, each time it was sent in recursively, was that offset went off even further by 1.
Okay, good. That's a good solution to a problem there. All right, so we change the offset to middle index plus 1. Then what do we do?
You recursively call it using the right part of the array.
Binary search with, so right slice of array and this new offset. All right, and if it's less, if value at middle index is greater than value defined,
Then you just recursively call. You don't need to touch offset.
you don't need to touch it at all?
No, because the index is still starting at the correct location.
With left slice of array,
I'm not sure about the +1 though, because our Dan and I's solution didn't use that, and I thought we got the right answer.
Well, we can try it both ways and see what comes out. All right, but it looks like we have some logic here, enough to get started at least. So let's try this out. So we're going to make sure it has value defined, array, and then offset equals 0. Then we say, first we have to sort the array. So I believe we can just do array.sort. I believe that's one that's array.sort changes everything in place, so we don't need to assign it to a new value.
Oh, I did see one other issue, I guess, because we're still trying to keep track of the previous offset. So on your pseudocode and line 7, we could either set it as a plus equal, or if you don't want to use the plus equal on line 7, we just do the previous offset. So offset equals offset plus middle index plus 1, or you could do plus equal middle index plus 1.
Like this, you mean?
Yeah, it's just that way. You know, that way you can kind of keep it in pseudocode without actually putting the plus equal.
Okay. All right, so we sorted the array. We need to find the middle index. So we could say middle index equals, all right, so we need to do the array length divided by 2. So len of array. So divided by 2 rounded down. So how can we, what's an easy way to round that down?
You could do double // or you can put an int on it.
Yep. So the double slash operator in Python just says divide it and then round it down. So we don't need to do any conversion from floats into integers, which is nice. I guess before we continue, I just want to make sure, does anyone have any questions about this pseudocode solution we did? I'm sorry, I should have done that earlier.
Don't we also, when you're doing your offset, don't you have to, never mind, sorry, I got it.
Okay. Any other questions? All right, so we have our middle index. And our next step says if value at middle index equals the value defined, return middle index. Seems simple enough. So if array middle index equals value defined, then we return middle index. Is that right? All right.
We would also have to, or we would have to return the middle index plus the offset, because otherwise, if let's say we're in our third recursion, it's going to be offset.
Yep, exactly. So that offset is designed to just the fact that if it's at position, I don't know, 3 in the original one, but it ends up at 0 in the new one, we don't want to return 0, we want to return 3. All right, so we return middle index plus offset. Right, we could say if len of array equals 0, we want to return -1. All right. So then we have if value at middle index is less than our value. So if
we had less than or equal to 1 would return for the length. If you got to
So let's think about this for a bit. So if we slice down our array down to 1, so there's two options that we can get if we reach that point. Yeah, what are they?
It could either match or it could not match.
Yeah.
Okay, so yeah, so we do have to kind of go back and test again. So I think we got lucky.
Yep, exactly, because we need to get, if we're at one option, we need to be able to test that one last one, and then if that doesn't work, then we can just cut it down to nothing, and then know we're done.
Okay, thanks.
Good question, though. And then we could say if middle index is less than our value defined. So if it's less than the value defined, it means that we need to get the right slice of everything. So we know we have to change the offset to offset plus middle index plus 1. All right, and then we need to get the right half of the right half. So how do we get that right half?
Using the array, we'll go ahead and use the bracket, well, open bracket, and then double checking here. We're just pulling off the middle index plus 1 because we're testing the middle index, so we know we don't need to send that in. So that's why we're gonna do the next element in, and then a colon, and then we could leave that blank because that will return all the way to the end of the list at that point.
Mm-hmm. All right, so just real quick, what does this colon mean exactly?
Go to the end.
Mhm.
Inclusive.
Yeah,
That's
there's a start is what the middle index would be filling in that position, the start. And then if we didn't want to go all the way to the end, let's say we wanted to stop at the second to last item, we could put a -2 there or -3. It separates the start value and the stop value in this slicing.
Yep, good. All right, so then we have to return binary search with this right slice array and our new offset as an argument.
A quick clarification there on line 20. You're right now you're testing the index, not the value at the index.
Very good. Thank you for catching that. That happens to me literally every time I try to solve this. All right, so if that happens, we want to return binary search with value defined, our right half, and then our offset is now going to equal offset. And then we can say elif array middle index is greater than the value defined. So in that case, we said that the offset doesn't need to change, correct?
Correct.
All right. So in that case, we can just find the left half. So we want to find, so what's the slice we want to take out of our left hand of our array?
Colon middle array. I mean middle index.
Colon middle index, like this. And what should that return us?
The start to the middle index, not including the middle index.
Mm-hmm. All right. So then we should just be able to say return binary search with our value defined, our left half, and then our offset is just offset. All right. So it looks like we've fulfilled every step of our pseudocode. So is this solution making sense to everybody so far?
We should have one more else statement. And maybe we left it out of the pseudocode, but starting in line 20, this is where we're basically testing the matching values.
Mm-hmm.
So if it's less than, we send the right slice. If it's greater than, we send the left slice. But when it actually equals, that's where we'll need to throw it as an else.
Mm-hmm. Well, I think we do that. We take care of that on line 15, actually.
For a middle index.
I think you want the if statement on 17 to be the first one, right?
Yeah, that's where, because we wanted to test the, like for us, in our base case, because we wanted to set the base case first, we're testing the length of the lists.
Mm-hmm.
And then we basically put your line 15, yeah, your line 15 and 16, we put that down at the end of the, we shifted it down about 12 lines, so that would go down to 17. But it should still work.
Yeah, this is, I think, in this case, you know, like assuming that, like thinking about our cases here. So we sort the array, we check if it's, you know, we find the middle index, and the math here should all work. Even if the array is empty, we can still run sort on the array, and we can still divide 0 by 2 without causing any errors. And then, so if we do array at 0 equals value defined, that might be a problem. Yes, so maybe we do want to make sure that we check if the length of the array is 0 first. That way we don't check any index numbers that don't exist. Then after that, we check, all right, did we find it? If not, then we get to these, the return, then we get to these. So yeah, I think in this particular case, whether we check our base cases first or these first, I think it should work either way, but we'll find out.
Isn't kind of philosophically that you want to check the base cases first, because that's kind of the end, right? I mean, you come in and hit the base case, then you're done. And if you're not done, then you start the recursion. It seems like logically the base cases at the top make more sense.
I find that's true in most cases. I don't want to make a blanket statement and say you should always do that. But in general, there's a lot can go wrong if you don't check your base case, if something can cause recursion to occur before you reach your base case.
Right, right, okay. And then just any quick comment on, we had made a lot of these else if, you know, the subsequent test says else if. Does that make a difference really? Any reason not to do that?
I don't think there's any particular reason to do that or not to do that. In this case, like for example, if I did if length array equals 0, then elif array equals that, the end result is more or less the same.
Yeah, I guess because you're returning from all of these blocks. If you
exactly,
weren't, then elif would be more, would seem to be just more efficient. You're not testing stuff. Yeah,
essentially every one of our if statements ends with a return. Right. In that case, if it hits the return, it won't even bother checking that. So we could also make this if like that, but I'm just going to keep it as elif because I think it looks nicer and is more demonstrative of what we're actually doing, which is check this one and then this one.
Right. Okay.
So, all right. Any other questions before I run our tests to see if they work?
Yeah, so we didn't, I guess this may be splitting hairs a little bit, but I'll say it anyway. So you guys are making a copy of the array. So if I'm doing binary search to avoid performance issues, I just made half of a very large array multiple times, especially using recursion, which is besides the point. So we ended up passing in a start and end array and never mutated the original array. We didn't make any copies of it.
Mm-hmm. Yeah. So there is a way to do this without changing, well, in this case, we're never actually mutating the original array except for the sort at the beginning, because we're just passing in slices of the array to the new function. So that doesn't change the original array in this case. But there is also a way to do that without actually passing in slices of the array. We can also just pass the array unchanged to every iteration, or every recursion. So this is one way to do it. There are multiple ways to hack it.
But also mathematically, you'd only, in essence, the amount of memory that you'd need to store one array, and besides what you call, I guess, the overhead cost, but the actual data itself, you're only going to have to do twice. So if you have a really large array, all the other small chunks will add up, but never get to the same size as the original array.
Also on the splitting hairs, we're sorting the list or the new slice of the new list every single time it's called. We're trying to do a sort, even though it's already sorted, we're trying to call the sort again. So it's it's running through that. But I think we can like conditional do a conditional on the offset, say like if it's equal to 0, then sort it, otherwise don't ever sort it again?
Well, let's say you're trying to find the number 1, and it's always going to be less than the middle until you get to the final case, assuming you're just like the sample was saying, hey, a random number between 1 and, or a random list between 1 and 1,000 or 10,000, or yeah, it was 1,000 list long, and I don't know. But if you're always constantly going to the left, the offset will never change from 0. So for us, we put in a flag as a optional. So like in the definition, we got offset equals 0. Our next one was need setup equal true as a default. And then when we recursively call the functions, we just passed in false into that. So that way, line 13 that's on the screen there, we'd replace that with if need setup, then do all that stuff. That would be the setup.
So I'm sorry, I'm not quite understanding. So how does the offset determine whether or not the array is already sorted or not?
Well, when you first call binary search, well, in my thinking, he was trying to explain exactly what I didn't think that far ahead of it. I was thinking that the first time you call binary search, your default parameter for offset is 0, and then every time after that you would be modifying it, but it looks like we're only modifying it in the case of line 23.
If the way I'm reading this now, as the way it's written now, assuming we have an unsorted array and we don't have this line, then we'd say, all right, if our array, the middle index of our array is greater than that, the offset doesn't change. And so we never sort our array that first time.
Yeah, but I guess to try to point it, it's not really going off the offset value. So if you did want to skip this on each additional recursion, because you did it the very first time, on line 12 in your definition, you would add another parameter. And we just say
sorted equals false?
Yeah, or as long as you know, we just put need setup is the name of it, and we set it to equal to true. So that way, your very first line after the definition, you could just put if need setup. So you can kind of read it English-wise, like, hey, if this needs to be set up, do this. Otherwise, you skip through. So, but we had a default value of true. In which case, if you want to use sorted equals false, then you'd say if not sorted, then do those steps 13 through, just 13 and 14. So if not sorted.
Something like that?
And that's all. And then down when you call the functions on line 24, you would just put in the opposite value of your default.
Yeah, or you could do the opposite of that and then leave it as the default as false, and then say if sorted is true, but then when you initially call it, you can pass in true.
Yeah, and you can do it either way. So, yep, this is a quick thing you can do for optimization.
Sorry, I didn't mean to go that detailed into it, but I was just thinking about sorting every time you're recursing.
Yeah, and it's good that you're thinking about that, because that is the kind of thing that you may be asked during a whiteboarding session. So it's good. All right, so I'm going to try running the test now. Oh, I need to get into the Python directory. I'm going to run the green version. So, all right, so we had 2 passes, 1 failure, and 1 error. So let's take a look at this. So let's see. The first looks like the first 2 tests has passed. And then let's see, what's the failure? So the first one we got 1 does not equal 2. And then this error one we got test array is not defined. Oh, okay, that's something we can fix. All right, so let's run this again, see how many errors we get this time. All right, so now we had 1 failure, but 3 passes. So if we take a look, this is test small array search 2. So that was this one. So when it tried to get 2, we were expecting, oh, wait a second. I think, oh, that's on me. I gave it the wrong. Okay, one sec. Let me try this. I gave this the one. I gave it the wrong value. That's why. Try this one more time. Okay, now they all pass. All right, so that looks good so far. Let's add one more to make sure it still works if it's the last item in the array. So if I look for 5, the answer should be 4. Wait, I already did that. Sorry. So
Have you done a -1? In other words, the answer's not found.
good idea. Let's do that. Let's call this one item not in array. Equal. So we get this one. We get this one 6 and self.test array. The answer should be -1. Get out of here. All right. 5 tests, 5 passes. So let's just add a couple more to look through this super big array. So I'll add this to my setup. Oops. So we have a larger unsorted array. And I'll just test this out with, so we do test large array. And let's give it one that is in there, which includes 7. And actually, I'm not sure what, all right, let's use, 7, and the answer should be 5 in that case. And then let's do one where it's not there. Test large array not found. Self.assert equal binary search. And say if we give it -1, the answer should be -1. I'm going to clear this out, run green again. All right. Looks like our solution works. All right, excellent. Does anyone have any questions about binary search and the way we implemented this?
Actually, I had one question, not specifically about the binary search, but going back on, I guess, the testing spec. Looks like you're doing a new function for each test, and then obviously within each one, it's a self-assert. Maybe I'm doing it wrong, or maybe I'm doing it slightly different, I guess. So what I'm doing is I'm doing like one test returns correct values, and I'll do like 4 or 5 different of the self-asserts. 4 or 5 of the tests all under one function, and then I might use another defined, test if the function returns a certain type, and then I have separate tests ran in that. But I wouldn't. Basically, like if you're to get rid of lines 26 and 23 and every other line on there and just kind of merge them all together, all your self-asserts, is that, I mean, it works, but is that what you'd recommend as best practice, or would you recommend doing it this way where each individual test gets its own definition?
So the advantage of the method you were describing is that it's faster in terms of like what you have to type, because then you don't have to define so many functions, and it'll still work. So if I just combine all of these test small array searches into one function and just have self.assert equal, self.assert equal, self.assert equal in one function, If one of those breaks, then that larger test suite will read as failure, and it'll tell me what went wrong. The advantage to making every test its own function is that we have to spend less time narrowing down where it failed, because if just this test fails, it'll have one red light here saying that particular test failed, and I don't need to look through, okay, which one of these tests in this suite failed. So
Okay, yeah, because I ran into that where, of the 10 tests, one of them failed or something, but I usually find out where just by doing the trace back. But I suppose that would actually make it easier if it'll say this particular thing failed. So okay.
Yeah. So in general, I'm a big believer in making everything as granular as you can possibly make it. Just because the more moving parts you create, the easier it is to narrow down exactly where the points of failure are. That includes testing and creating functions in general. Because if I just say, okay, one of my functions broke, I can fix that function, as opposed to this huge function broke and I need to figure out exactly where it broke. Any other questions about binary search? Did anyone have like a radically different solution that they want to talk about? Because again, this is a algorithm with many different paths to lead to the same point. Like this isn't how I solved it when I did it, for example.
No, could you just scroll back up to the top of that binary search? The setup doesn't seem to be working on mine. So.
You mean in the testing suite?
In the testing, yeah, please. Self.test. Oh, it's self. Okay, that's.
Yeah. So setup kind of works a lot like init does in a regular class.
Test array.
Okay. Well, if nobody has anything else they want to talk about, let's take a break. Let's take a 10-minute break. So be back here at 10:15, and then we'll get into talking about regex and destructive versus non-destructive functions.